right, let me go here and share. Okay, why can't it share my screen? You can't see the normal curve?
No.
It says it's sharing. All right, let's try it again. All right, look now and see. Can you see it yet?
Yeah, I see it.
Okay, excellent. All right, so today we are going to talk about binomial distributions. And we are going to be introduced to binomial and geometric distributions by using our M&Ms. So binomial means two. And let's pretend, for the sake of what we're doing right now, that suppose the blue M&M is defective. As randomly as possible, select a sample of 10 M&Ms and record the number of blue ones. So, dump your M&Ms into the cup, or you can leave them in the bag, just don't look, and then basically shake up the cup, and then pull out 10 M&Ms and put them on a piece of paper or something. And in this little spot, the first time you do that, record how many blue M&Ms you get. I got 0 the first time. All right, then put those back in, shake them up, and do it 5 total times. Don't put anything on the graph yet. Just fill in this tiny little table about the M&M. Make sure you shake it up really good so you get a good random sample. And we're not done yet, so don't start eating them. All right, when you're done, you're going to tell me. I would have you come up here and do this, but it'll be faster for me just to do it for us. I got 0 once, and then this goes by 2, so 2, 4. We're up to 4. Oh, should be on the 3 though. This is good. Yep. All right. So, Alina, what did you get for your 5 answers?
2, 3, 2,
2, 3, 2.
1, 4.
Okay. So I'm going to put, you got 2 2s and a 3, so we're like right halfway up there right now, and a 1 and a 4. All right, Carson, are you done?
Yeah.
What'd you get?
3 3s and 2 2s.
Okay, so that will take this 3 up to there, and then the 2 right there. And you guys can draw this in when it's all done. All right, Emma Salem.
I got 3 3s, a 0, and a 2.
All right, so the 2 should be halfway up. The 0 can now go up to 2. And the 3s will be another 1 plus part of 1. All right, so Sophia?
2 3s and 3 2s.
All right, so the 2 goes up to here with another 1. And the 3 goes up to there with a half. Or with, yeah. All right, Nathan?
I had 2 3 1 0 2.
2 3 1 0 2. Okay, so the 3 is going up to here. The 1 is going up to there. The 0, get a half a M&M there. And then the 2s, you got 2 of them. All right. So Claire?
4 3 3 2 2.
All right. So the 4 can go up to there. Grab 1 for the 3s. And grab 1 for the 2s. All right. Emma Smith.
I got 3 7 3 2 2.
3 7 3 2 2. All right. 7's way out there. 2 3s and 2 2s. And then we have Garrett.
4 4 3 3 2.
4 4 3 3 2. All right, so half a 2. Got another 3 and got a 4. All right, Ryan, what'd you get?
2 3 1 2 0.
All right, so the 0 is up to 4 now. The 2 is at 17. The 3 is at 21. And the 1, I think I got them all. Did I get them all? I think so. Okay, and I don't know why, what is going on here? Let me try something here. All right, Google Classroom. Not that anybody else cares, but I can't see Ryan. Okay, turn off the sound because you don't want to hear that. There we go. Okay, so you guys need to, on your chart, on page 18, at 0, go up to 4. 1 is going up to 3. 2 is going up to 17. 3s are going up to 21. 4s are up to 4, and 7 is at 1. So only go halfway up there since the y-axis is going by 2s. And if I add all those up, I get 4 and 4 is 8, 9, 10, 11, 12. So I get 12 and 21 and 17, which nicely adds up to 50. Look at that. Look at us go. All right. And I have to do something here. If I look at this bag, I can tell, ooh, seriously? This is an unexpected event. I don't know if you know this or not, but they only produce M&Ms in 2 different places in the country. Did you guys know that? And M&Ms are produced in Cleveland and in Hagerstown, New Jersey. So in Hagerstown, New Jersey, the probability of a blue is supposed to be at 0.25.
Like in one bag?
That's the mix. So in Cleveland, they put 13 point, ooh, there's a yellow. If this is state. Did I get it? I think so.
Yeah.
Okay. In Cleveland, red is at 13%, orange is at 20.5, yellow is at 13.5, green is at 19.8, blue is at 20.7, and brown is at 12.4. But in Hagerstown, which all of these bags I'm assuming came from, I had 2 or 3 more of these bags that I threw away at home because silly, stupid me thought, oh, no, wait a second. This does say Cleveland. Distributed by, it says Hagerstown here, but then if you look at the code, it does say Cleveland. All right, so we're going back with the Cleveland, which is 20.7. Why do they do that? I don't know. They used to have a website you could go and see the mix, and it was all the same no matter where they were produced. There were more than 2 companies, 2 plants in the United States that produced them. And then they took that off the website, and there were a whole bunch of teachers that got really mad at them because these things are used by statistics teachers for all kinds of experiments because we know the distributions, and it comes in very handy for chi-square. Any of you have taken biology, AP Bio, I think they use this for chi-square too. All right, so keeping in mind that the mean, the expected value is supposed to be 20.7, 20.7 would balance about right here. You can draw an arrow and put 0.207. So does our distribution look like it might balance there? I mean, this is a very small distribution. It's not too far off though, right? And there's a way we can figure that out. And I don't know, did we use the program EXV yesterday? Okay, so we're going to use that. So if you would open up your calculator. So according to the, we'll answer those questions here in a second. Go to Stat Edit and clear out your L1 and your L2 by just hitting the clear and enter button. And then I'm going to get rid of that. And I think I'm going to move this over so I can see what we have. So we have 0, 1, 2, 3, 4, 5, 6, and we go all the way up to 7. So put 0, 1, 2, 3, 4, 5, 6, 7 in the amount of blue M&Ms that we have. And the reason we just did a binomial experiment is because blue was bad, but all the rest were good. If we think of blue as being defective. So you can turn almost any situation into a binomial situation. Did you vote for Trump? Yes or no? Did you vote for Biden? Yes or no? Because there were more people running than just the 2 of them. All right, so what is the possibility that you got a 0? That was 4 out of 50, so just put in 4 divided by 50, and it will change it into the decimal for us. A 1 was 3 out of 50. Then we had 17 2s, so put 17 divided by 50. And we had 21 3s, 21 divided by 50. And we had 4 4s. We didn't have any 5s and any 6s, but we had 1 7. So that's what you should get as your distribution if you put it into the probability distribution. Now, why is that at 0.06, but that's at 0.02? Because that was a 3, Mrs. Garrett. Okay, we're in good shape. All right. So now I'm going to use this program EXV, to calculate the mean and the standard deviation for me. So my possibilities are in list 1, and the probabilities are in list 2, and I get 2.46 blues is what I would expect, with a standard deviation of 1.186. So how does that correspond with what we just did? I will get there momentarily. All right. So let's put mu sub x was 2 point what? 2.46. And what is my sigma sub x? 1.18.
It's 1.1867.
1.1867. Okay. So keep those up there for the time being. Visually, if we're, I guess we can't really put 0.207 there. That's not really, well, 2.46 is what we get for ours. We'll put this in at 2.46. We have to change that into a proportion. But there's only one way we can change that into a proportion. And what do we have to do for that? Does anybody know how we can change those expected values into proportions? We have to each count how many M&Ms we got. So count your total M&Ms. I counted my partially half one as just one, but you can either count it or don't count it, but come up with a whole number. And so I am going to go back to my editor. I got a total of 80 M&Ms. Everybody got a third of a cup, and I tried to shake it and wiggle it a little bit, like so it would be flat when I took them out of the bags. I would have bought separate packs, those, you know, bigger packs like is on your picture, but that's actually more expensive, and these guys are expensive enough. I think I bought 5 of these, and they're like
$4-something.
this party size.
Oh,
These are $8.80.
Those are, yeah.
$8.88.
The share size.
The family size is like $5. All right, so how many did you get, Carson?
I counted 88.
88. And Sophia?
81.
And Claire?
84.
Garrett?
80.
Emma Smith?
80.
Nathan?
90.
90?
Yeah, I must have
I want your bag.
Oh,
No,
yeah.
some of the bags might have been a little fuller. I mean, that's pretty
Yeah, I
close.
think I repeated it.
Emma Salem?
81.
And 73? Oh, you got shysted. All right, Ryan, how many did you get?
80.
All right. And I don't know if you knew, I sent that extra bag for your little brother.
Yeah, I was trying to steal it from him to eat it last night.
But he wouldn't let you have it. That's good.
He already ate it by the time I got to him.
Well, it's a good thing we didn't invite him to come to class today and do this with us. All right, so if I sum that up, I can do math, calculate, nope, math, let's do, I think I want to do calculate. I want to do math, sum. Where's my sum at? It's a list, so it's a list operation. That's what I want to do. Second list operations, I want to do sum. Where's just regular sum? Huh? Cumulative sum keeps adding the one to the next to the next. Oh, I know what I can do. Okay. I can do stat calculate one variable statistic on list 3. And that tells me it sums up to 817 M&Ms total. And so if we do, well, we took 10 randomly out at a time. And we don't know how many total blue ones there are in our population, but we can figure that out in a second. So, all right. We'll figure this out in a second. We know we have a total of 817 M&Ms. All right? And to find the probability of blue, now we need to do what? Count up the blue ones. So this is, right now, we're playing sort of God, because usually we don't know what we're searching for, inference speaking. All right. So we'll put this back into here. I'll go to list 4. Sophia, do you know how many blues you got?
24.
And Carson?
22.
Claire?
24.
Garrett? Emma Smith?
27.
All right. And we can't be eating them yet because we still have another experiment to do. All right, Nathan?
21.
And Emma Salem?
17.
And Alina? Pardon?
19.
19. And Ryan?
17.
17. Okay, so now let me do stat calculate one variable statistic on list 4. And that tells me that we had a total of 215. So what is 215 divided by 218? What's the proportion? I think it's going to be a little higher than the 20%. So 215 divided by 817, maybe. I get 2631.2631. So we're not too terribly off, and I kind of almost wonder if Cleveland changed its mix. And I can look that up, third block, and let you know tomorrow. What we're going to develop more likely tomorrow is these formulas, a shortcut way to do the mean other than what we did up there. And so if we do mu times p, and we had 817, and we expected to be 20.7 as our probability, we got a total of 215. We really expected to get 169.119. 169.12 is what we should have expected, with a standard deviation of the square root of 817 times 2.07 and 1 minus, 0.207, 1 minus 0.207 is almost 80. So if I do the square root of 817 times 0.207 times 1 minus 0.207, I get with a standard deviation of 11.58. So if we add one standard deviation onto that, we go from 170 like 180, 2 standard deviations. So we're almost 3 standard deviations out, which makes me think, well, A, it's a small sample size, and B, maybe Cleveland has changed its percentage of mixing. But something else we can do with what we calculated, how many did we sample? 10, right? We sampled 10, and 0.207 we're supposed to be what we got, and if you multiply that together, we would expect to get about 2, and we got 2.5. So that's not terribly far off. So that's a binomial situation. When you have a fixed number of things you're doing, which is 10, and they're either blue or they're not blue. All right? So now we're going to do on page 19, which you didn't have pull out of your binder. We're going to do the geometric one and see what a geometric distribution looks like. As randomly as possible, draw one M&M at a time. Continue to draw out M&Ms until you get a red one. And then record how many it took you until you got to your first red one. So you're going to shake them up and then pull them out one at a time. Don't look in your cup. So I got my first red one on the 7th one that I took out. Now I'm going to start a whole new trial. So make sure you mix them up. So now we're going until something happens. And these are actually little red M&Ms, but you can't tell that too well, so. And before we eat, let's count the number of red ones we have, so we know what that is. Well, I had it in my head, and then it left. So I gotta count them again. All right. Carson, how many red ones?
Definitely still counting. Give me a second.
Okay. Sophia?
13.
Claire?
Say 13.
You guys are playing cart golf or something to that effect. Garrett?
12.
Emma?
13.
Nathan?
22.
Nathan got a strange mix. And he got the right. That's no good. Emma Salem?
14.
4.
Yeah.
And Alina?
14.
And Carson?
I had 12.
And Ryan?
13.
All right, we'll need that in just a minute, just, for the heck of things. All right, Carson, what did you get on your 5 attempts of this?
12, 11.
Okay, hang on, because I'm going to do this. 12, 11,
19.
19.
Yes. And then 2.
Okay,
And 8.
all right. Okay, Sophia?
6.
All right,
1.
okay.
3.
Yep,
3.
yep.
7.
All right. Claire?
5.
Yep,
6.
uh-huh,
4.
okay,
3.
yep,
7.
okay. Garrett?
2,
Mm-hmm,
6,
okay,
9,
yep,
4, 9.
okay. Emma?
17.
All right,
8.
yep,
11.
okay,
1. And 9.
all right.
1, 8, 1, 4, and another 1.
How many red ones did you have?
22.
All right. Salem?
5.
Yep,
Another 5. 6. 2. And another 6.
Alina?
3. 4. 7. And 6.
All right, I already got Carson. All right, Ryan?
4,
Okay,
9,
all right,
2,
go ahead.
5,
Uh-huh,
and 7.
7 is your last one?
Yeah.
Nobody got 10, is that right? All right. So you guys on your graph should make the ones go up to 6. A bar of ones go all the way up to 6. And then the 2s and the 3s go up to 4. The 4s go up to 5. The 5s go up to 7. 6 and 7 both go up to 6. 8 only goes up 3. 9 goes up to 4. 10 doesn't go anywhere. 11 is at 2. 12 is at 1. 17's at 1 and 19's at 1. And you can start eating your M&Ms if you wish. I'm going to see if the reds came out close to 13% just because I'm curious, not because it has anything to do with this page. So if I do stat calculate one variable statistics on list 5, I get 142. And 142 divided by, what did we have? 817. All right, 142 divided by 817. 1.73 or 0.173. And let me see if that's closer to the we did red. No, it's closer to Cleveland. So I don't know. I'll have to take a look. We have a small class, so I'll put all the results together from all day long, and we'll see what we get. So I guess first off, to answer number 3, does the observed distribution follow the geometric distribution determined by p equal 1.3 or 0.131? We're a little bit high. How many should it take us? Well, it should, if we're doing geometric, it should take us 1 over 0.131. That's how many, and we're going to learn about these formulas. 1 divided by 0.131 is 7.63. So does this distribution look like it is balanced at 7? Totally could be. I can put that into my calculator and find out. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and Brian makes 10, and we did it 5 times, right? So this should be 500 total. Am I doing that right? We each did it 5 times, and there's 10 of us. There should be 50 dots up there like there was last time. All right, so let me do that on here real quick. So okay. Can anybody tell me what is one noticeable thing that is different between these 2 graphs? Fives went up to 7. 6s and 7s went up to 6. Eights went up to 3. 9s went up to 4. 10s weren't anything. 2 11s. 1 12. 13s, 14s, 15s, 16s. 18s. Okay. All right, what did I put starting. O1 and O2. All right, when I run our EXV program, I get the expected value of 5.78. So this is balancing at 5.78, and we would expect it to take us 7 M&Ms. So that's a little bit low. The standard deviation for this, and I hope you notice something about these formulas, so we'll take a look at that in just a second too, would be 1 minus 0.131 divided by 0.131 squared. And if I do that in my calculator, I get 1 minus 0.131 divided by 0.131 squared. And that is 7.11, which we are well within one standard deviation there, because if you take 711 away from there, you're at 0. So our answer is well within one standard deviation. All right, so let's take a look at this first graph. Where did this start? Where did our graph start? At 0. The geometric graph does not start at 0. It starts at 1, because to get an M&M, you have to at least pull out 1. So geometric distributions always start at 1. And geometric distributions are usually more skewed than binomial distributions. Binomial distributions are sometimes skewed to the left and sometimes skewed to the right, and sometimes they're normal. This one's a little bit skewed to the right because of this one way out here. If you took that one away, it almost would be symmetric. Our geometric distribution is always, geometric distributions are always going to be skewed to the right. Does that make sense to you? If you keep going until, all right? So that's something to take note of. So somewhere, we have some room. I think you have room underneath this little table on the geometric distribution. You can write down geometric distributions are always skewed to the right. The geometric formulas which, by the way, they give you on the AP test. It's on your bright green folder. The geometric formulas, that's the expected value, and the standard deviation, you can write it a couple different ways. I wrote it like this, but you can also write it like this. And that's what's on your sheet. Does that make sense to everybody, that you can simplify the denominator? So those are the geometric formulas. Take a good look at those and then look at the binomial formulas. What's different about the geometric formulas? Yeah, they're dividing, but something else. So yes, I like that the geometric formulas have divisors. But what else do you notice? You guys have them right there on your papers. You can see them easier than me going back and forth. What else is different about those formulas?
The
that what you were going to say, Sophia? Yep. Missing n, which is the number of trials. And it makes sense that we're missing the number of trials because geometric, you go until a success happens. So we don't know the number of trials in geometric because you just keep going and going until. It's not infinite. I call it indefinite. Like you just don't know. Eventually it's going to happen. Yes, it's theoretically possible for me to pick up this big red die and keep rolling it the rest of the day and it will never come up the number 3. But what's more likely? How many times in a perfect world should I have to roll this to be sure that I'm going to get the number 3 to show up?
6 or less times.
Should be 6 or less, right? Because it has a 1/6 chance. So that's why you get this fraction. 1 divided by 1/6 is 6. We would expect 6 rolls before it comes up the number 3. Although we know it could go on forever. All right, so let's go back to the binomial formulas or to the binomial page and write these things down. Binomial distributions. Could be bell-shaped or left-skewed or right-skewed. And the other thing we want to know about binomial formulas, which is the following. Expected value is n times p, and the standard deviation is the square root of n times p times 1 minus p. So the binomial formulas, we must know n. N is fixed ahead of time. All right? So binomial distributions are success or failure, and geometric distributions, you go until you have a success. All right, we are going to go to page 20, but you can start eating your M&Ms if you wish. So that's just a little review of what's going on, and I am going to, we're going to go to page 20 here, which looks like this. But yeah, you're allowed to. So what I'm going to show you today is back in chapter 1, we started with regular distributions. So this is a regular distribution. This is the lottery problem that we started with the other day. If you just take the answers to the lottery and put them in a histogram, this is what it would turn out to be. Because this was a random event, we could then make a probability distribution. So it turns out that it looks identical. The only difference from a histogram and a probability distribution histogram is that the y-axis has been turned into relative frequencies. But it's still going to have the same shape. Also, you can't turn every distribution into a probability distribution, only if it comes from a random phenomenon. So now, we're going to put it into a binomial distribution. We have these formulas, the top times the bottom type of things that we use today, and we have the formula for the standard deviation. We're going to change those into shortcuts by finding out if a probability distribution is actually from a binomial situation. And if that's true, so this is kind of like the third layer. We have distributions, all kinds of distributions, and then one branch off of a distribution is a probability distribution. That comes from a random phenomenon. And a subset of a probability distribution is a binomial distribution. So we're going to set this up, and I'm going to show you how we get these shortcut rules for mean and standard deviation. So the census report says that 25 or 27% of California residents are foreign-born. Suppose we choose 3 Californians independent of each other. There are 8 possible arrangements. Are you still with me, Ryan? Yep, there you are. All right, so we're going to write down all of these possibilities. We could have 3 foreigners, right? Or we could have foreign domestic. That means they came from the United States. They were born in the United States. Or we could go into California and pick 3 random people and get somebody born outside of the country, probably in Mexico, would be my guess if you're in California. Domestic foreign-born, or we could get domestic foreign-born. What are the other things that could happen? Foreign-born, domestic, domestic. Domestic, foreign-born, domestic. Or domestic, domestic, foreign-born. Or all 3 domestic. Those are all the possible things that can happen if you're doing, were you born in the United States or were you born somewhere else? All right? Okay. What's the probability of being foreign-born? 0.27, right? So this is going to be 0.27 times 0.27 times 0.27. The next one's down. It's going to be 0.27 times 0.27 times point. What's 1 minus 27? 73. Yep, 0.73. This one's going to be 0.27 times 0.73 times 0.27. The next one's going to be the 73 out front, 27, 27. Then we have 0.27 times 0.73 times 0.73. 0.73 times 0.27 times 0.73. 0.73 times 0.73 times 0.27. And finally, we have 0.73 times itself 3 times. All right. I'm going to call on 4 people. The first person, could you find out, that's Emma Smith, what 0.27, you're going to do this one. Emma Smith is doing that one. Alina's doing the next one, and what else does that help us with? The next 2 down, right? Because it's just commutative, and we know that it doesn't matter where that 73 lands, so Alina's in charge of the next 3. Claire, you're in charge of the FDDs, the 2 Ds and an F, that's Claire. And the last one is going to be Carson. You're in charge of the 73s. And both Emma Salem and Nathan, you are in charge of adding all these up for us once we get them. All right, so who was the first one? Emma, what did you get for 0.27 times 0.27, 0.27?
0.0197.
0.19, and that's all of them, right? That's all the decimals.
Oh, that's 0.019683.
Okay, so yeah, you need to give me every single decimal. So this is 0.019683.
Yep.
All right, and then, was it Alina next? Okay, what did you get for the next one?
0.053217.
And that happens for the next two also. And that's all the decimals?
Yes.
All right, and I think it was Claire, were you next?
Yeah. 0.143883.
And we have that, again, 2 times more. And finally, Carson, were you the last one, or is that Emma Smith?
No, that's me.
Okay.
0.389017.
All right, and Nathan and Emma Salem, right, are in charge of adding those up, and make sure you confer with each other before you tell me what it is. What'd you get, Nathan?
I got 1.
It should be 1,
Oh, yeah.
right? Because
Yeah.
this is a probability distribution.
I got 1 too.
Good. All right. So now we're going to put this into the probability distribution. If there are no foreigners, what is that probability? So if X is the number of foreign-born people, on that chart above, if we get no foreigners, what is the answer, Nathan?
0.389017.
Mm-hmm. If I get 1 foreigner, then that is these 3 combined. So, Sophia, if you could do 3 times the 0.143883 for us.
0.43161.
0.4349.
1649.
All right. And if I have 2 foreigners, and it's a combination of all those, which is going to be, sorry, it shouldn't have gone down that far. That. So it's going to be approximately 15, a little bit higher than 15. Garrett, take 3 times 0.053217 for us. 51. All right, and then finally, Ryan, if I have all 3 foreigners, what's the probability of that happening?
0.019683.
Mm-hmm. All right, very good. Okay, we still have a little time. We're going to keep going. Doing this the old school way, can I come up with the mean? So the mean is going to be 0 times 0.3. What did you say? I need to bring this whole thing over. You guys can see it, but I can't. All right. I'm going to bring you down here. Okay, I like that a little better. So 0 times 0.389017 plus 1 times 0.431649 plus 2 times 0.159651 plus 3 times 0.019683. So in the long run, if I go picking 3 Californians over and over and over again, My question is, how many foreigners would I expect to get in that? So I think we can all try that one. I could put it into that other formula, but it would certainly make the standard deviation easier, Mrs. Garrett. Is that what you guys got? So I would expect 0.81 foreigners. 0.81 foreign-born residents. Almost one. All right, well, this next one's really gonna, all right. So what do I want you to put down for this one? I would like you to put 0 minus 0.81 squared times 0.389017 plus dot 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 plus 3 minus 0.81 squared times 0.019683. And we're going to have to take the square root of that. And instead of making us suffer through that, I'm just going to cheat and find out what it was. 0.5913. So this is 0.5913. And if I take the square root of 0.5913, I get 0.76. We'll make it 9, 0.769. Foreign-born residents. So this is doing it the old school way, meaning what we just reviewed from 6-1. All right. So the last thing we're going to do today, because we're not going to do the binomial calculations, we're going to talk about that tomorrow, is we're going to complete page 21. So this is page 21. And I need to graph this. So I'm going to grab this. Actually, I'm going to grab this. I'm going to make a copy. Move that back up there. And let's graph that. Right here. So 0 goes up to 0.389. At 0, I should go up to 0.389, almost all the way up to 4. 1 goes up to 0.4316. Not quite that high. 2 goes up to 15, so that's going to be at about right there. And 3 goes up to 1%, so it's like right there. And this is what my binomial distribution will look like. It is very right skewed. But if we take a look at what we calculated, 0.18, does this look like it might balance at, 0.81? Does that look like it might balance at 0.81? Yeah. So this is a binomial distribution. So tomorrow we're going to accumulate that, and then we're going to start talking about binomial distributions, and you'll get a new packet. So you don't have a whole lot of homework tonight, just the C's from your multiple choice. The thing I want you to remember is that binomial has a fixed number. You have to know how many trials you're doing ahead of time, and geometric, you go until you get a success. So binomial, there's two things: heads, tails, true, false, right, wrong, left, right, blue, red, or blue, not blue in this case, stuff like that. All right, I'm not going to use your cups over again. If you have M&Ms left, you can put them in your little bag and take that with you. Or you can throw them out, because I'm not, unless you want to give them to somebody else to eat. That's up to you. Kind of frowned upon, so don't let me know you're doing that. All right. Thank you much. And I'm hoping your homework takes you like maybe 10 to 5 minutes or so. How many do you have to show work for? 4 of them? Half of them? Oh, and you get to skip a lot of them. So yeah, you only have 4 problems to do for homework. Woohoo! So if you haven't found a statistic yet for statistics in life, maybe look that up or finish that, because we'll start doing that next week.
Do you want to like share those with you, or what? Like write a document?
Just have something that, like, when I pull your name, I'm going to start that next week. You can come up and say, if it's something you want to show, well, if it's something you want to show up here, then I'll have you share it with me. Yes.
So can it just be like any statistic that we find?
Yeah, any event or something interesting that's going on right now.
That's like involved with some statistics or something?
Yeah. All right, Ryan, any questions? Okay, have a good day, and we will see you tomorrow.
Yeah. Thank you again.
You're welcome. Have a good day.
Oh yeah.
And, yeah.
You can tell these are fresh M&Ms. Don't you think? Compared to M&Ms that have just been sitting around for a while, the big bags usually taste fresher, I think.
Does it taste like